Can I just say something very quickly? Just something very quickly. We've been asked by some people to do a group photo, so why not? Let's. We only have 3 talks now, and then we have a group photo, and then an early tea, early coffee, because two presentations, virtual presentations have not materialized. So 3 talks, then we go outside for a little group photo, and then we have an early coffee and tea. I should also say, check the weather forecast for Finland excursion next week. Looks beautiful the whole week. For Ram, also beautiful for considering where it is. So showers, some rain, so 16, 17 degrees. Excellent.
Okay, we're back to our senses after the lunch. And we have keep going with the session of mineralogy. First speaker is Matías García Tudelal from Luleå University, and he's going to talk about the EDMs in Cabo Ortegal, North Spain. So happy days.
Good afternoon. I am a first year PhD student, as María said, I'm from the University of Technology, Sweden, and I'm going to show you the preliminary results of my thesis research. So it's called New Observations on PGE assemblages of the anomalously high PGE-rich chromitites from the Cabo Ortegal complex. So this is the content of this presentation. I am going to start with a short introduction. So the ultramafic rocks of the Herbeira Massif of the Cabo Ortegal complex, located northwest Spain, host chromitite bodies with reported PGE contents up to 13,000 ppb. The origin of these chromitites and their PGE enrichment has been interpreted as formed by successive injections of mantle-derived chromium and PGE-rich magmas into a crustal chamber, and more recent research suggests that the chromitites and their host ultramafic rocks were formed by the interaction between melts and a refractory Habsburgite in a subarc mantle environment. Despite the huge work focused on the geochemistry and petrology of these chromitites, little is known about the PGM mineralogy, since the last work was done more than 20 years ago. That's why we review the genesis of this PGM on the light of new interpretation. That's why we study the chromitites located at the upper part of the Herbeira Massif. Here the black star indicates the location of the samples, and these chromitites are mainly host in dunites. According to their morphology and chromite composition, they can be grouped into 2 types. The type 1 chromitite, which are massive polyform bodies here in the upper image, and they have chromium numbers between 0.6 and 0.63. And the type 2 chromitite, which are massive horizons, host in dunite, but they are intercalated with pyroxenite layers, and they have higher chromium numbers between 0.8 and 0.82. In these 2 diagrams, the chromite composition of both types of chromitites is similar to chromitites host in the mantle section of ophelites. With respect to the PGE content of both types of chromitite is over 2,000 ppb, and they show an enrichment in PPG relative to IPG, and especially shows an enrichment in platinum. This can be seen in the PGM assemblages, which are mostly platinum, palladium, rhodium PGM, and in situ observations on thin sections shows that this PGM occur as inclusions on the edge of chromite and in the silicate matrix. These are examples of inclusions on the edge of chromite. Here we have some platinum iron copper alloys with base metal sulfide, especially pentlandite and chalcopyrite with amphibole crystals, platinum palladium sulfides, probably bragite, cooperite solid solution. Here there's another example of platinum palladium sulfide with platinum palladium iron base metal sulfide. This is the same image. This is a detailed view of the last image. And we have found some sulfarsenites, probably of the Hollingworthite, Irarcite, Plattersite solid solution with iridium iron nickel alloys. Here, these small clusters. Here, there's another example of platinum iron alloys with porous textures on the edge of chromites. And these are photos of base metal sulfides, mainly pentlandite, but this pentlandite can occur with chalcopyrite and millerite. With respect to the PEM located in the silicate matrix, these are platinum palladium sulfide, small grains, and platinum nickel alloys, base metal sulfides, and we have found this complex grain with complex textures. And they show that they have a matrix of rhodium nickel arsenic, which is probably correspond to saccharinite. And these brighter grains are iridium iron nickel alloys. And also occur with some platinum iron nickel copper fine aggregates. In order to complement this observation, we have obtained PEM from hydroseparation concentrates. And then we have studied by electron microtube. So we have found sulfarsenites, especially Hollingworthite and Irarcite and Plattersite. This is an example of these chromitites. Also, we have found this complex grain with complex texture, and the matrix is mainly made of rhodium nickel arsenic, which has composition near from saccharinite. And we have found these small intergrowths, which are mainly made of platinum, iridium, iron, and nickel. But this composition were obtained only qualitatively due to the small size. Also, we have found this idiomorphic spherulite and unidentified platinum sulfarsenites. And also we have found these PGE alloys here in the corner. With respect to the PGE alloys, these are mainly platinum iron alloys with composition between isoferroplatinum, tetraferroplatinum, and tulaminite. And all of them shows porous textures, as you can see here. One exception about the composition is this grain here in this picture, which is more enriched in nickel and copper. So what tell us this PPG enrichment and the textures? Well, the PPG enrichment resembles to that from the type 2 chromitite described in Jose Maria's works. And the interpretation of this is that sulfide melts collected incompatible PGE, and these sulfide melts were segregated by immiscibility from small volume melts. The observation that the PE and PM's varying sulfides are located at the edge of chromite and at the silicate matrix support this hypothesis, and suggest that the segregation of the sulfide melt probably took place after chromite crystallization. And then, due to their location of this primary PM, they were easily affected by post-magmatic processes. And one example of this could be the porous platinum iron alloys, which could represent the accumulation of small nanoparticles of platinum, iron, nickel, and copper from hydrothermal fluids. And of course, these complex grains, saccharinite, for example, is mostly interpreted as formed by secondary processes. But what about these small intergrowth that they cannot be studied, for example, by SEM, EDS, or electron microscope due to the small size? That's why we obtain a lamella of the same grain by focused ion beam and then studied by transmission electron microscopy. This is the section that was put in order to obtain this lamella. And here I have TM EDS analysis. And this is an elemental mapping and shows that the matrix of this lamella is mainly made of palladium, arsenic, rhodium, and nickel. And the intergrowth are made of iridium, osmium, copper, iron, and some of them has some platinum and small amounts of sulfur. Here is also we studied one of these intergrowths here, And this is a high magnification, high resolution TIM image, and shows that this intergraph is mainly made of aggregate of nanoparticles. And these are different domains that can be seen here in this elemental mapping, which shows the upper part is mainly made of platinum, nickel, some iron, and the lower part is made of iron, copper, iridium, osmium, and ruthenium. Summarizing, these are the composition of the matrix: rhodium, nickel, arsenic, and palladium. And the composition of this intergraph is platinum, nickel, iron, and iridium, osmium, ruthenium, iron, and copper, the lower part. Finally, as conclusions, the chromite composition of the chromitite of the Cabo Ortegal complex is typical of chromitites housed in a mantle section of ophiolites. The high PGE content, especially platinum and palladium, and the observation that the PGM with base metal sulfides are located at the edge of chromite and at the silicate matrix, suggests that the PGM enrichment is related to sulfur arsenic rich metals that collected base metal and incompatible PGE, and these metals were probably segregated by immiscibility from small volume melts. And then these primary PGM were affected by postmagmatic processes, promoting a locally remobilization of PGE, especially platinum and palladium. Finally, the FIV and high-resolution TIM analysis shows that this complex grain that I showed before has nanoparticles aggregates with composition between platinum, nickel, iron, and iridium, osmium, ruthenium, iron, and copper, all of them immersed in a matrix of rhodium, nickel, arsenic, and palladium. Many thanks for your attention.
Thank you for the talk. Any question? We have plenty of time.
I will ask one. Thanks for the talk. I just have a question regarding your PGE alloys or platinum iron. Was it possible to produce some electron diffraction? No, I meant these the one you presented at the end with these.
No, we didn't obtain any electron diffraction.
Okay.
Yeah.
Would it be possible, is it to get some idea about the crystallography parameters to give them?
Yes, it could be possible to make some diffraction. Yes, yes, but yes, these are preliminary results.
Sure.
Yeah.
Thank you.
You talked of an arsenide melt there.
Mhm.
Yes, did I understand you correctly?
Sorry?
Oh, maybe. Okay. Can you hear me now?
Yes,
Okay. You mentioned an arsenide melt. Was that correct?
yes, sulfur arsenic melt.
Okay. Apart from the PGM you saw there, do you have any other evidence for the presence of an arsenide melt?
Well, I have a lot of sulfarsenites there, erythite, platersite, and collingwoodite, and these are the most abundant PM that I found in these chromitites.
Just to be difficult, what if it was a sulfide melt and it's concentrated, the PGMs crystallized from that, and now you've lost a lot of sulfur because it's all serpentinites?
Mm-hmm. Yes. Yes.
Question?
Yes, that is an option. Yes, you could have these sulfur and arsenic melts, and you form this PGM, this primary PGM, and then you have this secondary process that promote some desulfurization process, and you could get these alloys too.
Okay, thank you. Any questions? So we move to the next talk. Thank you. By
We go push